Hey y'all, it's Becca. I'm a math, physics, and astronomy tutor here at Chegg. If you ever need such a tutor, feel free to check out my profile down below. But today I'm going to talk to y'all about something called the Index of Refraction. Now, if you've ever taken an optics course, you will have heard of the Index of Refraction, and it's just a way that we can measure how much a light ray is slowed down by a medium other than a vacuum. So the Index of Refraction is given by lowercase n, and it is the ratio of the speed of light in a vacuum, which we know is c, to the speed of that same light in some other medium like water or glass, like a light ray trying to travel through a vacuum, and then suppose it hits a slab of glass. It's going to slow down just a little bit, and that light ray is going to bend just a bit. So the index of refraction is a way that we can quantify how much that light ray slows down. So in a vacuum, of course, the index of refraction is just going to be 1 because the speed of light in a vacuum, in that medium being a vacuum, is just c, and c over c would be 1. Air, turns out, is not that much different from a vacuum. There's not a whole lot to slow light down, so we approximate the index of refraction in air to be about 1. In water, the index of refraction is about 1 1/3 or 1.33. And let's say you had a slab of crown glass, the index of refraction would be even higher, about 1.5. So light slows down quite a bit in crown glass. So let's say you run into a problem where you have a light ray moving through the air. Let's say we have this laser beam moving through the air. And then it hits some water, maybe an ocean or a lake or something. And that light ray is going to bend. It's going to slow down just a little bit. The initial trajectory of that light ray is about here, an extension of this initial arrow here. But since the light ray has hit the water, it slows down just a bit, and that bends the ray just a little bit. And if we know the indices of refraction of the air and the water, and if we know the angle at which the light hit the water, we can find out how much that light ray was bent with respect to the vertical here. And this is called Snell's law. It's named after a Dutch astronomer called, his last name was Snellius. But in fact, this phenomenon was recognized far before Snellius was ever born. But he gets the name, so we'll call it Snell's law. All right, so what Snellius and those before him recognized is that if we know the index of refraction multiplied by the sine of the angle of incidence, this is what we call this, the angle of incidence, that is going to be directly proportional to the index of refraction of the second medium times the second angle, which is called the index or the angle of refraction. So we have the angle of incidence and the angle of refraction, both with respect to this vertical here. Okay, so let's say our angle of incidence is 30 degrees, and we know that the index of refraction of air is 1. So we have our 1 times the sine of 30. And we also know that our index of refraction of water is 1.33. But we've not determined yet the angle of refraction. So in order to do that, we can plug our values into Snell's law and solve for our unknown. Well, of course, 1 times the sine of 30 is just the sine of 30. And the sine of 30 degrees is 1/2. So we have 1 over 2 is equal to 1.33 times the sine of theta 2. Okay? So to begin to get this theta 2 by itself, we would divide by 1.33 on both sides. Okay? So now we have 1/2 divided by 1.33 is equal to the sine of theta 2. And to get theta 2 by itself, we simply take the inverse sine of both sides. So that theta 2 is the inverse sine, or the arc sine, however you prefer to say that, of 1/2 over 1.33, which, popping that into a calculator in degree mode, gives us an angle of refraction of about 22.08 degrees. So this gives us kind of an idea of how much that light ray slowed down, how much it was bent towards the vertical. So between the vertical and the new light ray, we have an angle of 22.08 degrees, whereas between the vertical and our incident light ray, we had an angle of 30 degrees. So that was deflected about 8 degrees towards the vertical. Okay, so this is an intro to optics and to index of refraction. If y'all need help with any of your optics problems, feel free to hit me up or any other physics tutor here on Chegg. Bye.